some kind of superposition. Y is the change in y is at some kind of superposition where it's like it's not 1 and it's not -1 either. You can't define it. You can't say that it's either or anything, right? So it's undefined. But your y value is defined. And so we also call those critical numbers too. And the reason we call both of those critical numbers, the whole point of critical numbers is to know numbers that are important, right? These are if you know the critical numbers of a graph of a graph and you know what those critical numbers are, whether they're a relative maximum or minimum, you can basically graph out the function. Those are the only ones you really need. So that's why we call them critical numbers. Those are the most important parts of the function, more or less, generally. So, I don't know. We could start doing problems. Are the only thing you guys learning? Is it just critical numbers? Just this stuff? You guys are probably doing y double prime too, right? You're probably doing double derivatives too. I should probably talk about those then. You guys are
Another question.
yeah.
I've been thinking through this. So shouldn't dx or dy be like a horizontal line because like x is going up like 1 and then like y is 0, right?
Wait. Repeat that. Are we talking about this right here?
Yeah.
Well, okay. Let's look at let's look at this a little more carefully. So if x moves, let's say 1 unit from this, right? If the derivative of this, the tangent line looks something like this, so the slope at that point looks something like this. And so if we move a little bit on, not that way, if we move a little bit on the y, if we move a little bit up, x on this tangent line, we're talking about this tangent line, right? If we're moving a little bit up, x is also moving too, right? If we move up on the y, let's say this is -3, and on this tangent line we want to move to -2, right? X moved, right? The x value moved to get to that value. So that means x is changing as y is changing as well. But if we look at the vertical line over here, oops. If we look at the vertical line, so right here, x isn't x is not changing right here. See, it's if I want to move, no matter what, uh, x is moving this way, right? And then it stops. It's starting to move backwards, but somewhere along the way, it's had to stop moving, and that's where the line is vertical, right? X is not changing here, but y is like infinitely changing. We don't need to move x to get to a different y, if that makes sense. Does that make sense? I can explain it a few other ways too,
Yeah, that makes sense.
right? And we can think about this other ways too. Um, actually, yeah, I won't. I'll talk about those a little later. But let me see if there's a better way of explaining this. I think that's the best explanation I can give. We can also say like, huh? We could so if if y dx dy is the change in x over the change in y, right? But in this tangent line, is x changing at all? Is our x value ever moving? It's always
No.
it's always here. Our x isn't moving, so there's no change in x in the slope of this point. So dx dy is 0 because dx is 0. It doesn't matter what dy is. Here it's infinite, right? Or well, yeah. Here it's it's infinite. So, but that doesn't matter because 0 over whatever is 0.
Yeah, I was just looking at like the whole graph, but I forgot that's just looking at like 1 point, right?
Yeah, we're looking at 1 point. Yeah. Oh, I also want to clarify. So dx or yeah, so the change in x and the change in y are kind of dependent of each other. I don't really have a good way of um, writing this notation wise other than using prime notation, which is kind of annoying. But the change in x, so when this graph is moving, actually no, I do have a good way of showing this. Never mind. So So dy dx is the change in y when we move a certain value in x, right? And that's independent from dx dy. These are actually yeah, so in terms of critical numbers, these are two different things. These are not the same thing. Because or you can look at them conceptually as two different things, because dy dx is if we move if it's the change in y with respect to x. So if we move a certain amount in the x, how fast are we moving on the y? And in this case, we're moving 0. In this case, we're moving like, I don't know, -2. In this case, we're moving like +1. So that's dy dx. Dx dy is if we move a little bit on the y, how fast are we moving on the x? So if this was a point and it was moving along this graph, how fast is that point moving if y is moving at a constant rate? And that's the key. Y is moving at a constant rate. It doesn't matter what that rate is because it's a ratio. If dy is 0.2, that means dx went smaller by a certain amount as well, right? So it's a ratio, so the value we get is the same. But if y is moving, no matter what, you can think of someone holding this point on a stick or something, and he's moving it upwards at a constant rate. How fast is that point moving on the x? That's dx dy. So that you can think about those conceptually, and you can think about it for any other variable too. Once you understand that critical numbers are dependent on the variables you're talking about, you can think about this with any other variables. So in the context of like packaging, which I talked about earlier, you can talk about the surface area as you change the x value or something of like the depth of your packaging, right? While keeping a constant volume. And now you can see when our change in surface area is 0 and our critical numbers, and you can find the minimum surface area. So that's okay. So I want to talk about why, and this is just a small thing. I'm just erasing all this just because I'm gonna talk a little more. But another small thing I wanted to add was that um shoot, what did I want to add? Critical. So the reason that critical numbers give us, can someone try and explain to me why critical numbers give us the minimum and maximum most of the time? You don't need to necessarily know, but it's good if you guys try and give a crack at it before I tell you.
Because like maximum always like there's always going to be the derivative as 0 because there's a change in direction. So like comparing all the values, finding like the highest and then the lowest number gives you maximum and minimum.
Yeah. So yeah, and that's pretty good. So essentially, right? If you have a minimum or maximum, and I'm just gonna talk about dy dx. You guys know how to think about it in terms of other variables now, but I'll talk about just dy dx right now. If y is equal to some function of x, and this looks really funny to people to most people because f of x usually we use interchangeably with y, but you can actually use this to say y is a function of x, which is, I don't know. Anyways, so where was I going? Oh, right. Okay, so if y is moving in a positive direction, if to have a maximum, right, y needs to be moving in a positive direction and then start moving in a negative direction. Because if it keeps moving in the positive direction, then you don't have a maximum, right? So and we know from IVC, this is why it was really important that you guys learned that if dy dx goes from a positive to a negative value, it has to go through 0 somewhere if it's a continuous function. And keep in mind, it has to be a continuous function. You have to think about it a little more if it's not continuous. But if it's continuous, you know that it has to be 0 somewhere, right? And when it's 0, that's your maximum. And then for minimums, right, your y is going from a negative, your change in y is going from a negative to a positive. We're not talking about the y values, we're talking about the change, right? So our change in y is going from a negative value, I'll do this in red, it's going from a negative value to a positive value. So it has to be 0 somewhere if it's continuous. And we're not talking about y values, right? So even, and you guys probably already know this, but I just want to make sure because this is something that people get confused about a lot, even though like on a test question or something, if you're uh, if you're if you have a parabola that looks like this, right, and you have your y is still moving in a negative direction even though it's a positive value. It's something that comes up on the AP test. I guess people get confused by that, but you know, your dy dx is still negative even though it is a positive value. That doesn't mean it can't be uh, it can't be um, moving downward. So that should cover. Oh, we need to talk about double derivatives. So let's do that, right? So if if dy dx is the change in y with respect to x, right, is equal to the change in y with respect to x, then, and this is just notation for y double prime, which is what you guys probably use more often, but uh, don't ask me why we put the square here and the square here. I honestly have no clue. I have no clue why. But anyways, so d squared y dx squared is the change in dy dx with respect to x. And this might be weird to wrap your head around, but it is really important to wrap your head around it. It shouldn't be something that you just like brush over. It does seem obvious, but at the same time, it can be weird. Like once you start getting to problems to wrap your head around it. But if you really don't get it, you should spend the time to just think about it. Think about what this actually means. And in the simplest terms, I can try giving dy, the change in dy dx is basically the change in how fast your y value is moving, right? So if we here, let me try drawing this in the best way possible. So let's say we have sine x. Sine x is probably a good one to go with. Let me draw that better. So let's say we have sine x, right? Yeah, so we have sine x. Our y value, our dy dx is constantly changing, just like our y is changing, right? So so you know, our y is changing. Obviously, you can see that, but also our dy dx is changing, right? So here it's some value, and here it's some value. That's not it at all, anyway, because it went through. Okay. So here, oops, here it is some value. So your dy dx is constantly changing as well. And you can think about it with tangent lines. You can also think about it as just how fast your y value is moving. Just like a car, it can accelerate. So you're changing. Let's say your car is moving upwards. Just so I can keep talking about dy dx, right? If your car is accelerating, your dy dx is changing. It's moving more positive, and so that's what it means when d squared y over dx squared or y double prime is positive. That's what it means. Is basically your y is accelerating upwards. And similarly, d squared y over dx squared when it's negative is your y value is decelerating. Does that mean it's moving downward? No. Your car, when it's moving, right, when it's moving 50 miles per hour and you put on the brakes, it's still moving forward, but it's slowing down, right? So that would be like right here. And we call those moments, so we call when we know when dy dx is equal to 0, it's relative minimum, maximum, or something, right? When we call when y double prime is equal to 0, we call those points of inflection. I should probably write that over there. We call those points of inflection, right? And essentially, points of inflection is when our y or our x or whatever variable you're thinking about is going from accelerating to decelerating. So it's not, uh, and this is why I use sine x, because right here. Let me try my best to draw this. It's gonna be kind of tough, but so let's start over here, right? Dy dx is 0, correct? So that means, but then it's getting larger and larger, right? So now it is positive, and here it's even more positive, right? So it's accelerating our dy dx. But once you hit this point, 0, that's the maximum your dy dx is ever going to get, and we can show that with the point by finding that being the point of inflection. So it goes from accelerating to decelerating. So that's the fastest your dy dx is ever going to get. From then on, it's going to start slowing down. It's gonna go here, then it's going to go here, and it's going to start slowing down. It's still moving upward, right? D squared y over dx squared doesn't really have any bearing on whether we're moving upward or downward. It's just about how fast we're moving upward or downward. So now it's slowing down. And so I want to ask a question to you guys. At this point over here, is dy dx, or what is dy dx, or actually I just wrote it. So dy dx is equal to 0, right? Is d squared y over dx squared equal to 0? If so, if not, or if so, tell me why. If not, is it positive or negative?
Isn't it positive because it's gonna go back down?
Well, if it's positive, it should keep here, let me try my let me see if I can. I'm gonna erase some of this.
I have a question about the car problem. So if you think about like the y double prime to be accelerating and decelerating, and then what would you consider just dy dx?
Your speed, your miles per hour, or something,
Okay.
right? And that's why we say dy dx, right? And in honors chem, if you're taking that, we do dimensional analysis. We can consider these some form of units, right? So miles per hour, right? That's like dy dx, right? This is just a per point miles per hour, if you want to think about it like that. Per point in time, I guess, because actually no, it would be per point in distance because we're taking it with respect. Okay, well, dy dt. Okay, this feels like I'm getting in the weeds a little bit, but we should probably call this dy dt since we're doing miles per hour. So, in a point in time, how fast? Or not how? Yeah, how fast is y moving? That would be your miles per hour. That was a bit convoluted, but I hope that makes sense. So yeah, so dy dx would be considered your miles per hour. You can be moving 30 miles per hour while applying the brakes, right? You probably would be slowing down, right? You wouldn't be 30 miles per hour for long, but you can still be 30 miles per hour while decelerating. Does that make sense? So going back to this question, if dy, let me see. So uh, if dy dx is um, moving upwards, it's moving in this direction.
Hold on. Would it be negative? Sorry, not positive. Would it be negative for that point?
Yes. Do you want to explain why?
Well, Mr. Shaya just said like no, because it's reached its maximum, for it to go down, it has to like the change in the slope has go down. I
Yes.
really don't know what.
Yeah, it's basically another form of IVC. We're basically just like how if dy dx is positive and then goes to negative due to IVC, right? If this is dy dx over here, right? If it's positive then negative, it has to be 0 somewhere. We know that, right? Right? So if we look at so it's not another form of IVC, but so scratch that. This well, dy dx is IVC, but y double prime, right, in this case is not IVC, so for scratch that. But if you look at this, right, what's the derivative of dy dx? Is it negative?
Negative number.
It's negative, right? Because how are you gonna, without decelerating, how are you gonna go from moving upwards to moving downwards? You have to decelerate, right? You have to, if you don't do anything, you're just gonna keep moving upwards. If you accelerate, you're gonna keep moving upwards at a faster rate. So you have to decelerate to move downwards, to go from positive dy dx to negative dy dx. And that's why it's also the double derivative we're looking at, because that dictates, because that well, I just showed that the derivative of dy dx is negative. So that's why we look at this to see if it's a relative maximum or minimum. I can explain it a little bit more if that doesn't make sense. Does that make sense?
Can you explain it one more time, please?
Yeah. So, okay. So, if does this make sense? At least that that it has to your the dy dx of your dy dx. So the change, if you pretend this is some function f of x, right? Just like ignore that it's dy dx. The derivative of f of x is negative, right? Does that make sense? For it to go from positive to negative, it has to, your derivative has to be negative. You have to be moving downwards in this function. Does that make sense?
Yeah, that makes.
Okay.
Yes.
And we know that this function that we're looking at is dy dx, or it's a representation of it. It's poorly drawn, it's probably not accurate, but we know that this is dy dx. So the derivative of dy dx, right, is, and this is convenient because since derivatives work like fractions, dy dx of dy dx is, if you multiply 5 times 4, it's 20. So dy dx of dy dx, right, is d squared y over dx squared. That's why we write the notation like this. Don't ask me why. Again, don't ask me why. That doesn't explain why the squares are in different places. I honestly don't know why, but that's why we look at. That's another way you can say why we're looking at the double derivative. Is there a question you have? Because that might help me explain it better if what I'm saying isn't making sense. Is there a specific question that you have about this?
I can get my textbook really quick.
Okay.
But if we look at like sin x, wouldn't the double derivative be positive at dy over dx?
At
Would
this
it be
point,
good?
well,
Yeah.
well, dy no, okay, so dy dx is 0. We can agree on that, right? At that point.
Yeah.
Okay. Well, and we know that right here it's positive, right? Can we agree on that?
Yeah.
And we know that right here it's negative, right?
Yeah.
So that means the dy dx had to change negatively to go from positive to negative, right?
Yeah.
That makes sense, right?
Yeah.
Well, we know that d squared y, we know that y double prime is the change in dy dx, right? So so the change in dy dx, or y double prime, has to be negative at this point right here, because it has to go from positive to negative. If it was positive, it would look, I don't know if I want to. Okay, you can see this in the corner, right? What I'm writing. If dy dx, if y double prime was positive, it would look like this, right? Because you would keep accelerating. If y double prime was, and if y double prime was 0, you would just get a straight, or that's not that straight, but you would just get a straight line, because your dy dx isn't changing, right? So if you have a positive dy dx over here, the change in dy dx has to be negative for it to go from positive to negative over here. So we know that at this point over here, our double derivative is negative. Does that make sense? I can try explaining it again. It is also something you just have to think about a lot as well when you're doing the problems. But if it does that make sense? Do you have a question about that?
Yeah, that kind of makes sense.
Is there something that like isn't like is there something that just doesn't make sense, even if it's only a little bit? Is there something that you feel unsure about?
Like, if you take the derivative of sin x, it would be cos x, right? And then if you take the double derivative of that, you would get negative sin x.
Yeah.
And then if you set that equal to 0.
Well, no, this is pi over 2. We're setting it at the x value, right? Well, okay, let's move this over here because those will have the same dy dx and y double prime, right? We're not plugging in dy dx equals 0 into our double derivative. We're plugging in the x value. Remember that our derivatives are also functions of x. So we're plugging in the x value, right? So you said y double prime of sine x is negative sine x, right? Well, we know that this is pi over 2. So what's negative sine pi over 2?
Negative 1.
Negative 1. So this is negative. We just showed that it's negative. But we can, I think the one thing that you are misunderstanding is that when we take the derivative, no matter how many times we take it, it's still a function of x in this plane. Right? It's still some function of x. So we're not. So if we want to find y double prime at this point, we don't plug in 0 because dy dx is 0. It's still a function of x on this plane. So we plug in the same x that of the point we're looking for.
Wait, so like what Shimon was talking about, like negative sine x equals 0, that would help you find the point inflection, right?
Yeah, that will help you find the point of inflection because we're setting the output of dy dx, the change in dy dx, or the output of y double prime, which is the change in dy dx, is 0, right? We're trying to find when the change in dy dx is 0, and that would be at these points over here, right? Because I just showed over here, right, that it's your dy dx, your tangent lines are increasing in slope, but then after they come past this point, they're decreasing in slope. So that means it has to be 0 here. Does that make more sense? Like, is there something that you guys are still unsure about? Because this is an important unit in terms of like wrapping your mind around like how things are changing. So if there is something that even is a little off about my explanation, you can tell me and I can try explaining it one more time in a different way.
I think I just need to think over it by myself.
I don't really understand why you put pi over 2 into the equation. Into the thing.
Okay, that I can explain. Is it okay if I erase this first? It is.
Yeah, sure.
Okay, cool. So when we take okay, let me finish erasing first before I start talking. So when we take so let me just do sine x here. I know that's not very good, but so when we do, so y is equal to sine x, right? That is a function of x. If we plug in an x at some point, we're going to get our y value, right? dy dx works in the same way, right? So cosine x, right? We need to plug in at an x value. This is basically a function where we say, hey, I'm going to give you an x value, I'm going to input an x value, and I'm going to get the slope of the point of our original function at that x value, right? So we don't care what the output of this is. We don't care that this is, we don't care that, okay, first of all, there's this, oops, that's not that tangent line does not look like that. It looks like this, but So we don't care that the output of this is pi over 2, or not pi over 2. We don't care that the output of this is 1. Let's say this is pi over 2. We don't care that the output of this is 1 when we're finding dy dx of this point. Do we? We don't care what this is, because this is about the change in y. It's not about our y values at that point. Right? So when you were finding the tangent line of a point, you didn't plug in 1 because the output was 1 into this to find the slope of this point. Right? You were finding the slope at this point in x. We're still in this coordinate plane. So we need to, if we want to find the slope, our slope looks something like this, right? I'll write this in. So dy dx, right? And that's cosine x, so it looks something like, shoot, I'm not going to be very good at drawing this. Come on. Okay. So it looks something, I don't know if that's 100% accurate, but it looks something like this, right? It's still a function of x. It still lies on this plane. So if we want to find the slope at this point, we don't plug in 1. We don't care that the output of this is 1. Does that make sense? I'll talk about double derivatives, but does that make sense? We're still plugging in at this point to find the slope.
Yeah, that makes sense.
Well, then shouldn't our double derivative work exactly the same? Right? It still lies. I'll use this color, I guess. That's a bad color. I'll switch that. Oops. Let me make that a little thinner. Okay. So that's gonna work like, and I apologize that these are all overlapping, but so that still lies on this coordinate plane, just like dy dx, right? So when we want to find the double derivative of our point, we're still going to plug in pi over 2. We don't care what the output of this is. At that point, it is what, like 0? But we don't care about that. That's not what we're plugging in. These are still all functions of x on this coordinate plane. So we're plugging in the point of the x value that we want all this information for. Does that make sense? We aren't doing this. I should put x's on this. We are not doing that. We are using x equals pi over 2 for all of these. Does that make sense? Is there a question about that? Because this is crucial. Like this is if out of all the things in critical numbers, this should be the thing that you understand the most. So if that doesn't make sense, let me know.
So you plug in a point instead of just setting it equal to.
Yes, because these are outputs, right? So if you want to think about it like this, right? Here is 0, right? Well, our function is 0 over here too, or our dy dx is 0 over here too, and 0 over here too, and it's 0 over here too. So if we plug in dy dx equals 0, what point are we actually looking at? Right? It's not about the output. These are all functions where you say, hey, give me a value of x, and I'll give you some value, right? I'll give you, I don't know, I'll give you some value, right? So these still rely on the same coordinate system that we use this for, right? Now here's the thing: if we set this equal to 0, we would find all the points of inflection. We would find, I'm running out of colors here, but okay, so if we wanted to set this equal to 0, like you're saying, is that what you're saying?
Yeah, because I thought.
Or no.
Issue.
Okay, wait. Actually, you keep talking first.
Oh, I was thinking that, like, because when I was doing the problem, I just said the double derivative equal to 0 and just solve it and then find like the point of inflection.
Yeah, you're finding the points of inflection. You're setting this equal to 0 and you're finding the x values. So you're finding these x values. That's not what we're doing here though. We have our x value and we want to find the outputs. Right? That's it. So we're doing so what you're doing is let's just think about this in some function, a linear function, if you will, right? You want the y value. Okay. So you want to find the x value where y is equal to 0, right? Forget about all this. I'm just talking about functions, right? This function over here, f of x. You want to find what you're doing when you're setting it equal to 0 is you are finding the x value where y is equal to 0, right? You're finding you have an output and you want to find the inputs that get you those outputs. That's not what we're doing here though. What I have is an input and I just want to find all the information about this point on our function. We're not doing points of inflection right now. I'm just finding the double derivative and the single derivative of a point. So we have our input. We want to find the outputs. When you set it equal to 0, you have a desired output, and you want to find the inputs. Your desired
Wait,
output.
can I
is the point.
explain this?
Yeah, you can.
Okay, so let's just take the point pi over 2. So at that point, you're saying like the y value is a positive number, but the slope of that is 0. But at the same time, like the slope is decreasing, and that's where the y prime comes in, right? Or y prime double derivative.
Yes,
right?
the
Double
slope
prime.
is decreasing.
Yeah.
And
then like let's just like, so if it was a point like negative pi over 2, then the y double prime would be positive because it's increased.
Yes,
No.
our slope is increasing. Yeah.
Okay. And also critical numbers, other than finding the minimum and maximum, what is the point of it?
I can get to that. I just want to make sure Shriman understands that what we're doing is we're just finding we're finding the slope and the change in the slope of a point. That's what we're doing. What you're doing when you're setting equal to 0 is finding the points of inflection, which I'm going to do in a second. But right now we're just finding everything about a point. Does that make sense why it's different?
Yeah.
Is there any questions about that? Because I
No.
okay. So when like Shriman, when he says when we're setting it equal to 0, we're finding the points of inflection, which are these over here. They're not going to hit, in this case, they all are at where they hit the x-axis. That's obviously not going to be the case because we don't care about the output of our original function. We don't care about that. We're just finding when it equals 0. And that's also, before I keep moving on, that's also why when you take the derivative, constants go away, right? They go away when you're taking the derivative, right? When you add a constant, because we don't care. The derivative and the double derivative stay the same even if the function moves up, right? Up or down, right? And if there's a constant here, that also goes away because if the rate of change, if our slope is up here or down here or a little bit less, that doesn't matter to our rate of change of the slope. Just like how the slope isn't affected by how high up the function is, right? Does that make sense? I forgot where I was
That
going.
makes a lot of sense. That's like an aha moment. Yes, it makes a lot of sense.
Okay, cool. So where was I going with this? Do you remember what I started with the whole point? Oh, the whole point of that was to just explain why coincidentally it's just a coincidence that they hit the x-axis, right? But essentially, when we're finding that these are at the x-axis, or not, what am I talking about? When we are finding that this is equal to 0, our double derivative, we're finding the points of inflection where our slope goes from increasing, right? So it's going up and up. Our slope, I'm not talking about the y values, I'm just talking about the slope. It goes from increasing and then it goes to decreasing, right? And we can actually see that if you look at our red function, because that's our dy dx, right? Look, those are actually the maximums and the minimums, our points of inflections of our y prime, right? Because our y prime is going from positive to negative. Oops, actually, Shoot. Yeah. Our y prime isn't going from positive to negative. Sorry about that. It's our y prime is going. Wait. Hold the phone. I am. My brain is. Okay. So yeah. So okay. So our y prime is going from, it's going up and up, right? So that our y prime here is bigger than the y prime over here, to now after this point over here, it's going down. So our y prime over here, which again is the slope of our points, right? Is the tangent line. It's going from up here, so it looks like this, to down here, so it looks like that. It's less steep. So okay, now where was I going with that? So so the points of inflection are also the maximums and minimums of our y prime, obviously, right? Because we can just call this g of x, right? And just like how we took y prime to find the minimum maximum, g prime of x will be our minimum maximum of this function, right? So it's obvious, but it's also just something interesting to know. And then the reason we don't go past d squared y dx squared is honestly just practical, because if you think about it, triple derivative is the change in the change of our function, which is like, double derivatives are already pretty hard to wrap your mind around. Triple derivatives almost have no bearing on the actual function, because the whole point of taking derivatives is to find more information on our actual function. But after you keep taking more and more derivatives, you're gonna lose, like, it's gonna stop being useful. So that's why we stop most times. Once maybe once you do more advanced calculus, even, I don't know, maybe we do take more derivatives, but for now, that's why we stop at double derivatives. Okay, so are there any questions? Because I feel like I might have missed something, but are there any questions about anything? Like, even if so, I can let me see if I can. I'll do some like practice problems. They'll just be little thought experiments to make sure you guys are solidified on this. But are there any questions until then, or like, are there any questions about this right now? If not, then let's do a little bit of practice, and then we'll go to like actual problems that you guys have questions on. So, and actually, like, before we get back into like a lot of theory, this is actually really useful if any of you guys are doing computer science. This is actually the foundation of how machine learning algorithms learn, because essentially how they learn is that after they've done a bunch of training, we evaluate their accuracy, right? So it could be like 87%, right? And instead of using a percent, most of the time we do something called a loss function, which basically our loss, right? So if you have 10 losses out of 100 tries, that's a ratio, right? That's 0.1, right? So you want to get that loss as low as possible, which in this case is 0, right? Depending on the loss function you use, it could be different. But in this case, we want to minimize our loss. And we just figured out how to find the minimums of functions. Our loss is a function that we can derive, and it's really complex math. But at the end of the day, we're trying to minimize it. So they actually use calculus to figure out how to change our model so that we're minimizing it. We're moving in the direction of a minimum of our cost function. So when AIs are improving, they actually have no clue what they're doing, right? It's all white noise in their head, right? All they're doing is minimizing. They're just playing a game of minimizing their loss function. So, calculus is in a lot of places. So, anyways, okay, let's do a little practice problem. And these are a lot on your theory test, because a lot of people don't spend the time to wrap their minds around this stuff. So let's say we have a point right here. Is dy dx positive or negative? And is our double derivative positive or negative at this point?
Both of them would be positive.
Yeah, because if you want to look at it, right, at our tangent lines, they are increasing, and our y value in our original function is increasing as well. So they're both positive. Now let's look at, I can draw another one. Let's look at I don't know, let's look at maybe, okay, how about, I'm just gonna, that is not a function, whoops. That is just sine. Let me, sorry, my brain is blanking a little, but, okay. This one's a little different, but in a circle, what is dy dx, and what is dx dy? I'll go back to doing the other ones, but this is just something to get you thinking.
Would dy dx be negative while dx might be 0? Or like a vertical line?
So dx dy is 0, right? And for dx dy to be 0, dx has to be 0, right? Because this is a number over a number, right? A over b. If that's equal to 0, a has to be 0. Can we agree on that? So if dx is equal to 0 in this point, right, with respect to y, if dx is equal to 0, if the change in x is equal to 0, then dy dx is equal to some number over 0. You can't have a number over 0, though, so it's undefined at that point. And you can look at this in a more conceptual way. This is a more like rigid proof way, but you can also look at it like, well, if we move our y value by a certain fixed amount, our x value isn't really changing much, right? So this is 0. It isn't changing at all, but like since you move it, yeah, it isn't changing at all, right? And you can look at this on a tangent line. No matter how much you move up in y, our x is not changing. So that's why that's 0. But if our x changes, there is no, like, x could move a little bit. It doesn't mean anything for x to change anymore because y is just on this line and it's changing infinitely in all directions. It's meaningless, right? So that's why it's undefined. It's almost like y has an almost infinite velocity here. If x is moving at a constant rate, right? Y dy dx goes from here to completely vertical, right? And at this point, y is moving infinitely upwards. So technically, you can say, okay, this is infinity, right? Because x is moving. If you go a little bit less, right here, x is moving positively still, right? So you could say it's infinity. But the reason we don't call it infinity is because if you go this way, or x starts moving backwards, right? Shoot, yeah, is this a good way to say it? Yeah. So x is starting to move backwards. Well, it's probably the other way around. Oops. So as y, so we're going to go back to dy dx for a second. As y is moving, we probably want to think about it this way. As y is moving downward at a fixed rate, x is going from moving this way to moving this way, right? So how do I say this?
Hold on, where did you get infinity from?
Oh, I was saying, okay, yeah, actually, that's where I was going. So you get infinity because as you go, as you get closer this way, right? So at this point, it's getting steeper, and then you get closer, and it's getting even steeper. So like, if you weren't thinking, so from a limits perspective, as y, y gets, or as dy dx as y gets close, limit of dy dx as y gets close to 0 from the negative, so from this way. Let me erase some of this. Oops, not what I want to do. So as y gets closer this way, our slope is going to go to infinity. But we don't say that it's equal to infinity because on this side, it's going to negative infinity. Now, if we say the limit as y goes to 0 positive, now it's negative infinity. Do you see how our slope is? I should probably have used different colors, but do you see how our slope here is getting steeper if we pick points up here instead of down here, right? We're still getting closer on this point, but now it's going to negative infinity. So you have a similar case to absolute value x, where on one side you're going one way, and on another, so like on this side you're going to 1 no matter how close you get, and on this side you're going to negative 1, but at this point it's undefined because you can't say which one it is. Similarly, we say this is undefined because on this side over here we're going to negative infinity, but on this side we're going to positive infinity, so you can't say it's either. So that's why we call it undefined. And another way of showing that was over here, where I said, okay, if dx is 0, dx dy, right? If dx dy is equal to 0, can we agree that dy dx is equal to 1 over dx dy? So that's 1 over 0, which is undefined. So that's another way of thinking about it. This is a more conceptual way. Does the conceptual way make sense? I can try explaining it a little bit better.
No, it makes sense.
Okay. So, all right. So that was so you can think of it like if you want to turn off your brain a little bit, I guess you could just say vertical line is undefined. But the reason it's undefined is because when there's a vertical line, your dx dy is 0. Like you can try however you want. If you draw a graph, dx dy will be 0 when it's a vertical line. Dx dy, I'm talking about dx dy. It'll be 0 when it's a vertical line. So dy dx, which is 1 over dx dy, you'll get 1 over 0, which is undefined. So, shoot, where was I going with that? So yeah, that's why it's undefined. There's a lot of ways of thinking about that. But so that's why you can think, okay, if it's a vertical line, it's undefined. If you want to, think about it like that. But you should know the underlying reason why it's undefined. And it's because as you get closer to that point from different sides, your dy dx isn't going towards the same point. The limit does not exist. So it doesn't exist. So it doesn't exist at that point, the value. For vertical lines specifically. Because if you wanted to draw out here's actually a good way of thinking about it. If I wanted to draw out dy dx of this, it would look like, let's say this is x squared plus y squared is equal to 1. So this is 1, this is negative 1. You would have asymptotes here, right? For dy dx. I'm not talking about dx dy or anything. I'm talking about dy dx. You would have asymptotes here, and here you can see it's horizontal, so you'd have 0 here, and then here you get negative and positive. So it would look like, how do I do this? It would look like this. It looks really weird, but it looks like that, right? And you can see actually at most x values, dy dx doesn't exist. So you'll notice when Mr. Shile gives you a problem, like find dy dx of the circle, he'll give you both the x and y value of that point. because otherwise you have two. If you're given just the x value, you have two different y values you can find the derivative of. And if you look at dy dx, there's two different things. So you can't. I guess you could say plus or minus, but yeah. So anyways, that was all to say that you can basically think of vertical lines as undefined because they're asymptotic in the derivative.
He said, quick question. You guys go on for, do you guys start at 6:30?
Yeah, we've been talking about this for a while. There's a lot to go over with critical numbers, but I think
Oh, okay.
I think it's worth it because we did get like a really high level explanation, I think, of everything. We'll get to questions, like if you have specific questions, we'll get to those right after this. I'm gonna actually. Does anyone have any questions on this before I erase it? If you do, go ahead and ask. That's fine. I can explain. But okay, so this makes sense for everyone. It was a bit of a really long-winded explanation, but did that make sense? Does someone want to actually let's have someone try, someone who was here for the whole thing, do you want to try explaining this in your own words, kind of? I gave you a few
Quick question.
Oh, yeah.
Right. What else did you guys go over? You guys went over.
We went over critical numbers with the first derivative, and then we went over critical numbers with the second derivative. And now we're talking about critical numbers with different, depending on how you are finding the derivative. If you're finding dy dx or dx dy. We're just doing little thought experiments because this point is this unit is probably the most theory-based unit out there. So.
Oh really?
Yeah.
Okay.
So anyways, does this make sense? I want someone to try explaining it who is here. So either Shriman or Harshita, if you guys could try explaining it in your own words before I move on. I gave you a few explanations, so there's even an easy one if the others don't make sense, but
But this has been recorded by the way.
yes, I did not. I forgot to record like the first 5 minutes, but after that I was recording. So.
Okay.
Are you guys there? Are you guys comfortable with explaining?
What do you assume? Sorry, oh sorry, Richard.
No, go ahead.
Okay, yeah. Shrikar, you can go ahead, and then Harshita, I want you to try explaining this.
I just had a question. Is like if the organic chemistry tutor, in your opinion, would probably go over these?
Maybe. I don't know. I haven't really. I maybe used him as a resource for like pre-calc back when I was learning that, but I don't think I've watched his calculus stuff, so I don't know if he's good at that. But there's this one guy, his name's 3 Blue, 1 Brown, or something like that.
Oh yeah.
He's pretty good. He explains everything in pretty good detail. So yeah.
Okay.
So anyways,
Thank you.
okay, so Harshita, I want you to try explaining this.
Well, I guess the most simple explanation is at that point, when we like find the slope, it would be a vertical line because the y value isn't no, the x value isn't changing. So you would just do a vertical line, and that means that like when there's a vertical line, the point or the slope would be undefined. Or another way to think about it is that you're going from like two opposite sides, right? Like going one above versus one below. And that means like the limits of both of those would be like negative infinity or infinity. So that means that dy dx would be fine because they're not the same.
Okay, cool. That's mostly complete. Just one thing I wanted to add. Dx dy, right? The derivative of x with respect to y is 0 at this point, right? So, and we know that dy dx is 1 over dx. This is probably the most simple explanation, right? Is 1 over dx dy, right? So, but that's 1 over 0, so that's undefined. So that's why this is undefined. Actually, one way, this is probably, I think I just probably came up with the easiest explanation, which is, let me redraw this. This will only take like 2 minutes. I think this is a pretty good explanation. So, So essentially, you have a circle, right? Well, that's not a very good circle. Okay, that's better. So dx dy at this as you approach from this side, right? Is x moving positively? So as you go from here to here to here to here to here, as you get closer to this point right here, is dx dy is positive, right? Our change in x with respect to y as it's moving at a constant rate this way is positive, right? Because it's moving this way. Even if it's slowing down, it's still moving this way, so it's positive, correct? Make sense?
Just the x value?
Yes, the x. On the x. This point on the x dimension has a positive velocity, right?
Yes.
But if we keep moving, remember, we're moving y at a constant rate downwards. So this way, now dx dy is negative, right? It's moving this way. Went from going this way to that way. Does that make sense? Do you see that? The points are progressively going downwards this way, right? And it's going from moving this way, now it's moving farther and farther this way. Does that make sense?
So this is illustrating dx over dy?
Yes, this is dx dy. This is dx dy I'm talking about right now. So as we're getting closer, I'm going to call this point A, where the vertical line is. As we get closer to A the limit of dy over dx. So keep this in your mind. Dy over dx is equal to 1 over dx over dy, right? So dy dx, the limit as y goes to 0, because in this case the vertical line is at 0, right? As y goes to 0 from the positive, so it's coming down, so we're talking about this region over here, right? Dx dy is positive. It's a really small number, but it's positive, right? Still moving to the right. So what would that limit be? What would this be? One over a really small positive number. It's
Infinity.
infinity. Yes, so this is infinity, but the limit as y goes to 0 from the negative of dy dx is, because it's going negative here, right? As we get closer, it's still moving in the negative direction.
0.
0. Yes. Or no, it's not 0. It's 1 over a really small negative number.
Is it
Oh,
just negative?
Negative infinity. So the limits are not, the limit approaching from both sides is not the same. So it's undefined, right, at that point. Does that make sense? That was the simplest explanation I could offer. It
Why
works.
did you choose to make it like arrow go down rather than up?
Well, if you do it up, it doesn't matter. Again, dx over dy, it's a ratio, right? If I multiply both sides by 2 or -1, which would change the direction y is moving in, dx dy also changes, right? Now, here, this is actually a good question. This is a really good question. Watch. So now, if we move positive, now it's moving down here, it's moving positively, and now it's moving negatively, right? If we move this direction, correct? So this is just going to flip it. Now this is going to become negative infinity, and this is going to become positive infinity. It's still undefined. No matter how you slice it, it's going to be undefined at that point, upwards or downwards, at whatever rate you choose. Does that make sense? I just chose downwards because it was easier to draw, or it's the first thing that came in my mind, but you can do it upwards as well, just like I showed. Does that make sense?
Yeah.
Because at the end of the day, dy dx or dx dy is a change in one variable with respect to another variable, this bottom variable. So we have to think about the change in this variable with with a change in this variable, with a change. So we need to define some kind of change in the bottom variable to think about it. And most of the time, like for dy dx, we say, okay, let's say x is moving positively. That's how we're going to measure our change. Positive 1 specifically. That's what dx, or that's what our change in x is, right? 5 over 2, or a slope of 4 is 4 movements up on the y for every 1 movement out on the x, right? So it's it's just we picked a defined movement on the x, right? But it still doesn't change, right? If we multiply this by -1, it's still the same slope. It's just shown differently. Does that make sense? Is there any questions about that? I thought that was pretty elegant, but maybe it's not. I don't know.
The upward direction makes sense, but I'm a little confused how you got like dy dx when it was like going down. Like if it's infinity or negative infinity.
So dy dx, oh, it's positive. That's why I put it in red. So when it's moving downward, it's this. Does that make sense? Is that what you're asking?
Yeah, I don't understand about that.
Well, we can think about it like, let's say, let me erase, if I can carefully erase. Oops, no. Okay, that's the best I can erase it. But let's say we're moving down like 0.001 on the y. So that would be a negative 0.001 change in y. Negative 0.001 change in y, right? If we move down that little bit, x is moving, let me zoom this in, right? This is a zoomed in illustration. That's a really bad zoomed in illustration, but right? If we move down a certain amount in y, so that's negative 0.001, right? Shoot, let me put this on the point, right? So negative 0.001 on the y. Which way is our x moving? Our x is moving out this way, right? It's like a 0.0001 change in x, right? Does that make sense? Keeps going. I just didn't want to draw the rest. I'm like zooming in on like a point over here with a certain change in y, which I defined to be moving downwards, right? Negative 0.001 change in y. Does that make sense? Up to so far? Your answer.
So shouldn't
Oh, keep going.
so shouldn't it be negative infinity since it's like a negative over a positive?
You might be right. Let me see. Negative over a positive. Yeah, I think you are. I think these flipped? Yeah, they are flipped. Okay. Yeah, these are flipped. These are flipped on the when we're moving downwards. You're right actually. And then if we are moving upwards, this becomes positive infinity, and that becomes negative infinity. Good catch. I didn't realize that. Because as we're moving down on the y in negative direction, our x is moving outwards, so it's going to negative infinity. And then as we're moving downwards on the y over here, it's moving backwards on the x, so it's negative over negative, so it's positive infinity. And then it's reverse for moving upwards. So that makes sense. So you were right about that. So
Yeah.
are we all on the same page here? Is that good? That was the best explanation I could give for why vertical lines are undefined. I don't know why I even went down that tangent line, but does that make sense?
Yeah, it does.
Okay, cool. I'll do one last little thought problem. This shouldn't take long at all. This is gonna be just normal, but let's say our function is let's do this. right? And let's pick this point. What's dy dx? And what's or is it, actually, I shouldn't ask you what it is exactly. Actually, yeah, I can. Let's say I say dy dx is equal to 0 there, right? So this is, that's a bad tangent line. So this is, like that, is d squared y over dx squared equal to 0 as well, in that case? If you know it, I think I should, I'm gonna ask Shrieker to answer this just because he wasn't here, so I want to make sure he's on the same page. But, what do you think? Is it 0 as well? Our double derivative? The change in our in the slope?
I think it would.
Yeah. Do you want to explain why?
The reason is as if the slopes on both sides are where the dx dy is equal to 0, then the double derivative of dx dy, the slope it would be like
Wait, a dx dy or dy dx?
sorry, dy dx, not dx dy, a dy dx.
Okay.
And then I would, because if you see the graph as it approaches a point, if you were to take the double derivative, if you see, it's like essentially taking the derivative of a horizontal line.
Yes, but if we take the derivative, let's say we have sine x, right?
Mm-hmm.
We're taking the derivative horizontal line here, but our double derivative isn't 0.
Okay.
Because if you,
I'm not sure.
Because the funny thing is, right, like sine x, if I want to find the derivative at pi over 2, I don't plug in pi over 2 and then take the derivative of a constant, because then it would always be 0, even over here, which doesn't make any sense. You first take the derivatives, then plug in your stuff. So that's actually key. So our double derivative does not care what our derivative is. It does not care. Like, it won't. It does not care. Like, it's its own separate. It's derivative of our derivative, obviously, but like it's separate in behavior from our first derivative. So the reason that, actually, do you want to explain why, Harshita?
Explain what?
Why this is 0?
Oh, I was just thinking because like the slope of the horizontal line would also be 0.
Okay. So it seems like you and Shrieker are on the same page there, which is good, because then I can just explain it to both of you. So the easiest way I can explain this, right, is essentially, let me draw the tangent lines. Let me do those in red, actually. Let me draw the tangent lines. So as we get closer to that point here, what is happening to our tangent lines? Oops. What is happening to our tangent lines over there?
It's approaching 0.
Is
Or
it
like
increasing?
getting less steep.
Is it increasing or decreasing? Are the slopes
The
increasing?
Slope is decreasing.
Okay, does everyone agree that the slopes are decreasing? So let me draw a coordinate plane over here for dy dx. So if our slopes are decreasing, actually, d squared y, I should probably draw that in blue then, wait, or green, I'll do green. So our double derivative, right, our change in our slopes is negative in that range, right? I'll just draw a single point. It's negative in that range. It's decreasing, right?
Correct.
Now, if I look at the tangent lines after, what's happening to them? Increasing. So that means it's up here.
Oh.
And we know from intermediate value theorem, which is why it was really important at the beginning of the year, that it has to be 0 somewhere in between. And we know, and this is obviously, you could argue, okay, maybe it's like right over here instead, or over here, but like it's likely 0 at that point. So you know, actually, you would probably say it has to be 0 at that point. There has to be a point of inflection at that point, right? It can be a point of inflection at another point. There could be a little dip and then like that before it goes up, and I'm not drawing that, right? It could look like that, but it does have to be 0 there because our slopes are going. Actually, no, it it doesn't. Never mind. Never mind about that. So does that make sense? Why it's 0 there? And that's what we call a point of inflection. It's basically a critical number. If you, oh, one second. Let me draw this first.
Okay, go ahead. There.
So if we draw dy dx, right? It's negative and it's positive and decreasing, right? So it's like this. And then, oops, maybe I should draw it like it's like this, right? And here I'll draw this, and I'll draw that, so we all know we're talking about the same point, right? This is essentially a minimum for our double derivative as well at that point, a point of inflection. So it's when our it's basically a point of inflection. You can also think of it as a critical number for your derivative. When it changes. When it changes, though, it has to change. If this goes from if this goes from, and this will be on your theory. This will probably be on your theory. If it goes like this, that's your double derivative, or not your double. This is your single derivative, a hypothetical one. This isn't a point of inflection, even though it's 0. Your slope of the derivative is 0 because it's still going downwards after. Right? That would be actually, and I guess if you want to talk about like triple derivatives, that would probably be a point of inflection for your triple derivative, which is not really useful. Like we don't like it's not really useful. But for our double derivative, right? It didn't go from decreasing to our, how do I explain this? Our shoot, wait, I might have done a flawed explanation. Let me think about this real quick before I open my mouth again, just to make sure. Oh, you know what? Yeah, I did do a flawed explanation. Ignore everything I just said there. If our derivative is going like this, and then it hits, and then it keeps going down, right? Where'd it go from negative, or where'd it go from, wait, my brain's blanking. Give me a second. Okay, so where'd it go from? So it went from positive to negative, right? But that's not a point of inflection because it didn't change our that would look more like, and I'm gonna draw the hypothetical in blue. This is our hypothetical, right? That would look more like this. That's not a point of inflection because it didn't go from decreasing. Our slopes didn't go from decreasing to increasing. They just keep decreasing. There's nothing special about that, right? Does that make sense? So it's not just a point of inflection is not just when and this is really important actually. I know I've been like talking a lot, but like this is important where if your double derivative is equal to 0, that doesn't necessarily mean it's going to be a point of inflection. If it goes from positive to negative or negative to positive, then it's a point of inflection, right? Because it inflected. If it just goes from positive, hits 0, and comes back up, our double derivative I'm talking about, then it's not a point of inflection because it's still gonna it didn't do anything. Does that make sense?
Kind of. The only thing on the top when you were referring to dy dx is equal to 0 and how you know you were showing like the slopes of the lines. I still don't entirely understand why the double derivative would equal to 0.
Well, well, if it goes from negative to positive, it has to hit 0 somewhere, right?
Okay. Oh, okay. I see. I see what you're saying.
Yeah, and that's interesting. So that also means, if you
Whenever the concavity changes.
yeah, you can think about it when the concavity changes from negative to positive. That's also why if it goes from positive, hits 0 and comes back up to positive, the concavity didn't change. So that's not a point of inflection. Does that make sense for everyone?
Wait, I have two questions. So my first question is like this might be really dumb, but since it's a change, like when we're doing right, so like the f of x graph, since it's the change and like y over change in x, since and we're only like using one point, what is the other point that we're using to figure out that change?
The other point. Oh, well, that's our limit. That's where our limit definition comes in, right? Our other point. Let's say we have a function. We define the derivative to be the slope between 2 points as, let's call this point A and point B, as B gets infinitely closer to A, right? So there's actually 2 points, but they're so close together, it's theoretically 1 point. That's where your limit definition came from. The limit, let's call this x, and this is x plus h, right? The limit as h goes to 0 of f of x plus h, your slope formula, you know where it comes from, but like f of x plus h minus f of x over x plus h minus x, which is h. So that's where you're taking. Does that answer your question?
Yes, yeah, that clears it up. And then the second question is, can you like explain the concave up and down and how that relates to point of inflection?
Okay. So let me. Is it okay if I? Actually, okay. I'm gonna erase a few things, but I won't erase it all. So I'll erase that, and I'll erase that, and that, and that, and I don't know if I want to erase that. So if we have a function like this, our slope is always decreasing, right? It started here, it's decreasing, right? We're saying it's always decreasing if you keep moving this way on the x, right? So we call that concave down. And if the slopes are decreasing, what does that tell us about concave down? What does that tell us about the double derivative of our concave down function? If the slopes are decreasing.
It's slowing down? Wait.
Yes. Well, not exactly. Well, okay, so it means that our double derivative, d squared y over dx squared, is negative, right? Because it's our slope started some value, right? Started at some value. Shoot, that's probably not a good way to show it. Our slope started at some value, and it just keeps going down. So that means the change in our slopes is negative, right? It's going down, the slopes. Does that make sense?
Yeah.
Okay. So then for concave up, which is something like this, right? Where our slope goes from here, and then it goes to here. That's a little less steep. Then it goes flat, then it goes up. It's going up, our slopes. I'm not talking about the y values of the function. I'm just talking about the slopes. The slopes are going up, right?
Yeah.
So what does that say about our double derivative here?
It's positive.
Yep. So for points of inflections, the way we define it is when it goes from concave down to concave up. But the problem with that is you can't just assume every time our double derivative hits 0, it goes from negative to positive. It can bounce off, right? It can go from, I'll draw this blue as our double derivative. It can go from positive, hit the 0, and then go back up. It doesn't have to go negative after it hits 0, right? And that's not a point of inflection because it didn't go from concave down to concave up. In this case, it always stayed concave up, right? And this is our double derivative, right?
Yeah.
And this isn't, by the way, this isn't the double derivative of anything I showed. This is just a random one. So, so if it does that, it is not a point of inflection, right? Because it didn't go from concave down to concave up because it didn't go from negative to positive. Correct?
Yeah.
So that's all I was trying to say was that you want to find where there's 0, but you also want to make sure they go from positive to negative as well at that point. It goes from positive to negative or negative to positive. You want to make sure it crosses that the axis, the boundary, and doesn't just bounce off for it to be a point of inflection. That's just how we define points of inflections. Because it's not really useful to know that it hit the x-axis and stayed concave up. I mean, I can try drawing it, but the difference is so subtle. Let's see. This is going to overlap with that graph, so it might be hard to see, but it'll look like this. And that. It looks exactly the same. Actually, like, I wouldn't even be able to tell a difference. No one would be able to tell a difference, right? The only way, like, it increased, and then it stopped increasing for a while, so it stayed flat like this. Actually, yeah, that's a good way to show it. So, let me, this is going to be tiny, but, the only thing that tells us that is relatively useful is, like, it did this, and then it stayed flat, like, perfectly flat, and then it started going back up again. Do you see that flat region right there? That's all it would tell us. But the thing is, since it's only a point, there is no flat region. So it's literally useless. Like, it doesn't affect anything at all. Does that make sense?
That makes sense.
Yeah. So, okay, so that's mostly... Okay, I'll do one last one, and then we'll get to problems. So honestly, at this point, you could probably figure out most of the problems for yourself once you revisit them. But I can do a few. But let's just do one last problem, and this one will be quick, I think. So something like that. You can think of it maybe as an exponential function or something, right? At this point, is dy dx positive or negative? And then is d squared y over dx squared positive or negative?
Negative for both?
It's negative for this one, but if you look at the tangent lines, it's pretty steep. It gets less steep, and then it gets less steep. Oops. And then it gets less steep here. So your slope is actually increasing. It's still negative, but it's actually increasing, right? It's getting less steep. So it's actually positive. Does that make sense? It is something you just have to, like, do the problems and think about every single time. Like, make sure you're thinking about this stuff while you're doing the problems, so that this starts to make more sense. But does that at least make, like, a little bit of sense?
Yeah. Okay, because it's going from, like, a negative, like, approaching 0, I guess. So that means that it's...
The slope is approaching 0. Yeah. So you can think of it. You can think of it as a car that's moving. Let's say this is in a different axis, right? So it's not the x-axis. Let's pretend it's the y-axis, but I laid it flat, right? You can think of a car. It's moving this way, or it's actually moving this way, right? But it's slowing down. So it's going negative maybe 15, and then a second later it's going negative 14 miles per hour, right? It's actually increasing, right? It's negative, but it's increasing. Let's say you're applying the brakes, but it's not gonna. If you're applying the brakes, it's not gonna go positive, right? It's just gonna go to 0. It won't go positive if you apply the brakes. So this is a similar.
Okay.
Yeah, so it's similar in that like it's increasing, but it's never going past. That's why it looks. That's why there's an asymptote here. And our double derivative, the change in our miles per hour, or the change in our velocity, is it's it's increasing, even though our velocity is actually negative. And a good way to think about it is like, if you can in your head, imagine a point with a tangent line kind of stuck to it, and imagine like moving it along this, like back and forth in your head, and the tangent line's changing along with it. If you can do that in your head, it might take a while. You might need to do more problems before you can do that. But if you can imagine that, it's pretty helpful. So
Yeah, I mean, I was like visualizing like all the dy dx lines, and I still like just thought that like of all the lines, the slope would be 0, but I didn't think how like it's changing. So okay, that makes sense.
yeah, it's another level. You've learned about how the slope of the point, or the velocity, is negative or positive, but you never. So the position of the point, you've learned about how the position is changing, right? And you can measure that. Now you need to go like one step further and think about how the change in the position is changing. So it's another. That's why practice in this unit is the most helpful. It's going to make it so much easier for the other units as well. So this is something you want to make sure you're doing a lot of. Okay, now I think we're good enough to go to any practice problems that you think you still can't answer. Because I think if you revisit them, you can probably answer most of the ones. But if there's any that you like still think you don't know how to do, now's the time for those.
I haven't done the homework yet, so I'm not sure.
Oh, okay then. Okay, so this should be good. Make sure when you're doing your problems to like keep this in mind. Like even if you get the right answer, you want to go back and look at the problem and analyze it in terms of the derivative and double derivative and see if you can piece it all together, right? And actually, I'll leave you before I talk about that with one last thing. The reason we look for critical numbers is so we can better graph functions, which I think he might have already showed you that you can do it with that. But if you have like the main points, right, you can say this is a relative maximum and y double prime is negative, and you have this over here, and it's a point of inflection, and then you have this over here, and it's a relative minimum, and y double prime is positive, right? You can kind of you can graph it out just with those critical points, right? That's my best graph that I can do. But like that's why they're called critical points, because they're like the most important parts of the function. So, anyways,
I have a question
oh
about
yeah,
that actually. So if we have like 4 critical numbers, right, and then 2 of them are like relative maximum and relative minimum, the other 2, how would you know if there is a change in direction? Is that just based on the next point, or is there a way?
a change in direction for the slope or for the points, like the position.
The point, the position.
So like, how do I know that it goes up and then down? Is that what you're saying?
No, I'm saying like because if there's like 4 critical points, right? So when the derivative is 0, and like 2 of them would be like relative minimum and relative maximum, what would I do with the other 2 critical points? Like, is that even possible?
Could you give me an example? I'm gonna put like you can tell me some arbitrary points, like their
Okay,
coordinates.
so like 1, 2,
Okay, so I'll put that right there.
and 3, 4.
Are those, wait, 1, 2 is that, what critical number is that?
Do like that was my question, because like Mr. Shio, he drew like a polynomial graph, and then it had like 5 critical numbers, and so how do I know? My question is like, if I have like,
The function, how do you know how many critical numbers there are?
yeah, that's just like factoring it out, right?
Yeah,
Oh,
factoring
okay.
out.
I have a question. Hold on. I have a
Okay.
question with me. Okay, so it's saying that like y prime equals x minus 1, x plus 2, x minus 3, and x minus 4 squared.
Wait,
Do you want me
so
to repeat?
yeah, could you repeat that?
Okay, y prime equals x minus 1, x plus 2, and x minus 3, x minus 4 squared.
Okay. Well, and okay, and he's just telling you to draw a potential one. That's all.
Well, it's just true or false, but I just want to know, like, how would you graph this?
Oh, like the original function. Okay. Well, if you remember, when you take the derivative of a function, constants go away, right? So if you want to find the original function, there's actually multiple ones, right? You can add whatever constants, right? So there's actually an infinite amount. But we can draw a potential one. And one way to do that is I would recommend first drawing the function. So first I would actually draw what I call a y prime line. So, and I would put all of our zeros. So 3, 1, -2. So if we go before -2, this is, I think if you had Mr. Nelson for pre-calc, he would have showed you how to find like the intervals. But this is x squared, x cubed, our leading term is what I'm doing right now. It's x squared, x cubed, x to the fourth, x to the fifth. So that's our leading term, right? So we know that past -2 it's positive, and after 4 it's, or past -2 it's negative, after 4 it's positive, right? Because x to the fifth. And this is the derivative. It's not the original function, right? And then we can alternate. There's a reason that it alternates, but for now I'm just gonna, you can probably figure that out yourself with a little bit of experimentation, but it alternates except when you hit a square, it'll just repeat. So now that you have that information, you can draw out dy dx, which I'll draw out right here. I should probably have done this in red, but I think it'll be fine. So that's -2, 1, 3, and 4. Okay. So at -2, and this is our this is the derivative. We're not thinking about rates of change just yet. I'm just straight graphing the derivative. So it's negative, then it goes positive, then it goes negative, then it goes positive, then it bounces off and goes positive. So that's what our derivative looks like, more or less. We can only do an approximation with this information. Well, we could do more exact, but we don't need to. You probably would. Actually, right now, I'm not going to do it, but you could probably take the derivative again if you wanted to and find points of inflection. I'm not sure if he wants you to do that. Actually, what is the question even asking? Is it asking to graph it, or what is the question asking?
It's not asking to graph it. It's just like true or false questions, or like is relative minimum at x equals
Oh, okay.
-2.
Well, okay. Well, if he wanted you to graph it, he'd probably give you the points of inflection too. So keep that in mind. But for now, let's just pretend that like I don't care about the points of inflection. I'm just doing a rough sketch. So we know that, like, let's say -2. Let's say that also hits the x-axis. We don't have that information because c can be anything, right? -2 could be up here, it could be over here, it could be over here. It doesn't matter because the derivative will be the same, right? That's why constants go away when you take the derivative. So I'll just say -2 is over there, and then 1 is like, since 1 is a relative, it goes from positive to negative, our slope, right? So it's if you want, you can also do this on your y prime line. You can say, okay, the slope is negative, then at -2 it's 0, so it's positive, so it's negative, so it's positive, then it hits 0, and then it's positive. I'm drawing out the actual function. That's what it looks like on my y prime line. And then I can do it in the bigger graph and say, okay, well, let's say it's, and then like that, and then it keeps going up, it keeps going up, it keeps going up, and then at 1, it's 0, our derivative, so it's a horizontal line. Dy dx is a horizontal line, so it goes down, keeps going down, and keeps going down, then it hits 3, right? So it's a horizontal line, then it goes up, then it goes up, and then it hits 4, right? And okay, I probably should have drawn 4 a little bit farther. So let's say 4 is over here. It becomes 0, but then after it goes positive, because if you remember, it repeats, right? So our slopes are still positive. And that would actually be a
Inflection before then?
yeah, that would be a point of inflection. And the reason for that, I mean, if you look at what I drew over here, 4, it goes from negative to positive. Like if we look at the critical numbers, so pretend this was f of x, our derivative here goes from negative to positive, right? So we know it's a point of inflection versus these other ones where they stay positive, right? Right? So that's why we know that one's a point of inflection. Does that make sense why we know it's a point of inflection?
Yeah, yes.
Okay, so that's a point of inflection. And yeah, so that's a rough sketch. Obviously this graph can move up or down, and like the exact like curves I can't draw because I don't have any more information. I could, if you put this in a calculator, it would probably brute force it by plugging in a bunch of numbers in between, right? But since he's probably not going to ask you to do that because that's just unnecessary work, this is the best approximation I can give. So that's kind of what it looks like. Does that make sense how I got there?
Yes, it does.
Okay. And if he hasn't taught you that yet, he'll probably teach you that next week. So, yeah. So that's, unless you have more questions, we can end it. I think you should be good for everything that he's teaching you so far.
Yeah.
Okay. All right, cool. All right. See ya.
Yep. Thank you.